In the last lecture, we looked at radiative transfer in enclosures containing gray diffuse isotropic surfaces. We will now look at situations where the assumption of a gray surface is not good. We saw earlier when looking at radiative property surfaces that there are many materials which cannot be assumed to be gray, that is, their emissivity and absorptivity are functions of wavelength. Now, that immediately causes a problem. So, I will take a few examples today to illustrate how the spectral variation of properties of materials causes very unusual situations, which is not encountered when you deal with gray surfaces. The example I am going to take is a Dewar flask. All of you have seen it in many situations where people carry liquid nitrogen in these flasks to their laboratories. See, these are essentially containers which contain either liquid nitrogen or liquid oxygen or hydrogen, and they are like thermos flask, but of a larger size. And they are used to, let us say, store liquid hydrogen or liquid nitrogen. And these are at very low temperatures, typically below 100 degrees Kelvin. And so, you will imagine that from the ambient heat will leak into the flask. And the main purpose of this Dewar flask is to cut down the amount of heat leaking from the outside into the flask, because as the heat leaks in, the liquid will start boiling and will lose liquid. Now, normally if you had looked at heat transfer literature, generally is believed that heat leakage in this case will be proportional to the difference between the hot temperature and the cold temperature. So, this is the well known Newtonian cooling law, which says that the heat transfer from a hot surface to cold surface is essentially proportional to the temperature difference. So, if this is high, then you will expect the heat leakage to be high, and vice versa. This is true in most situations. As the temperature difference between the hot and the cold object increases, more heat is transferred. But today you will see that in the Dewar flask case, there are unusual situations wherein the heat transfer is not proportional to the temperature difference. Not only that there are situations wherein as the temperature difference increases, the heat loss actually. So, as the temperature difference increases, the heat leakage decreases. So, this is completely counterintuitive result, goes against all the previous understanding of the nature of heat transfer between two surfaces. So, this shows that radiation heat transfer has some unusual features which make it different from conduction and convection heat transfer. In conduction and convection heat transfer, in most situations you can be quite sure that if the temperature difference between the two objects increases, then the heat transfer between them by conduction or convection will be larger. So, to encounter a situation here wherein the radiative transfer can decrease as the temperature difference increases is what is called a paradox. So, our aim will be to understand this paradox in the context of what you have learned so far about the way emissivity variation varies with wavelength and temperature, and how radiation is exchanged between two bodies. So, just to recapitulate, Dewar flasks are used to store cryogenic fluids like nitrogen, hydrogen and helium. The boiling point of hydrogen is 20 degrees Kelvin when the pressure is 1 bar, while that of nitrogen is around 76 Kelvin. Now, if these liquids are carried in Dewar flask, and the ambient temperature, the surroundings, is around 300 Kelvin room temperature. Then the difference between the ambient and the hydrogen containing Dewar flask is 280 degrees Kelvin, while that between the ambient and the flask containing liquid nitrogen is about 223. So, by normal wisdom you would expect the heat transfer into the Dewar flask containing hydrogen to be larger than that containing liquid nitrogen, because the temperature difference is larger. But it was found by experiment that this was not so. So, laboratory observations show that heat leakage into the flask with liquid nitrogen, which has a lower temperature difference, is about 60% more than the heat leakage into the Dewar flask which contains liquid hydrogen. So, the question is, why should heat leakage be higher when the temperature difference is lower? So, this is the issue we want to address and understand from radiation heat transfer. So, to do that, we treat the Dewar flask as a simple two parallel cylinders. The inner cylinder is a temperature T2, which is close to the boiling point of hydrogen or nitrogen, and the emissivity of the outside surface, which is silvered, is epsilon lambda 2. So, we are reminding ourselves that the emissivity of the surface is not constant, it is not gray, it is a function of wavelength. Similarly, the inner surface of the outer cylinder, which is also silvered, is epsilon lambda 1, and the outer temperature is T1. So, our aim is to get an expression for the heat leakage from the outer to inner cylinder through radiation when the emissivities of the two surfaces varies with wavelength. Okay. We had discussed this issue when discussing the radiative properties of surfaces, and since we are talking about here silver surfaces, silver is a metal, we had discussed quite in detail how the emissivity of metals varies with temperature. So, let us see how this will. Now, the simplest way to understand the heat transfer between the two surfaces is to do simple ray tracing. The radiation emitted by surface 1 reaches surface 2, is partly absorbed, the remaining part is reflected, and it is reflected back to surface 1 again. So, one can add up the total number of photons arriving from 1 to 2 and being absorbed at 2 as an infinite series, the direct contribution after 2 reflections, 4 reflections, 6 reflections, so on, and this standard ray tracing technique, and this is how it looks. The radiation absorbed by 2 from that emitted with 1 is a infinite series, and finally, the net radiation exchange between two surfaces can be written as follows. So, this result derived by ray tracing could also be derived by using the electron analogy. So, this is a well known result. Now, this result is very simple, and because in this result we are not allowed for the variation of emissivity with temperature and wavelength, and so this result can actually be expressed in a simple way in terms of Newtonian cooling law. So, the standard law that comes from convection is heat transfer coefficient times temperature difference. In the case of radiation, if it is a two black surfaces, it will be T1 to the power of 4 minus T2 to the power of 4. You can expand it, and you can see that these two terms do not vary that much when you vary T1 and T2, because this is in degrees Kelvin, while the real difference comes in here. So, many people write Q radiation also as a radiative heat transfer coefficient times temperature difference. Okay. So, they make it look like convection. So, if this was true, then the heat transfer by radiation should be proportional to temperature difference. But this does not happen in the case of the Dewar flask. The Dewar flask, it is found that when delta T is higher, the Q rad is lower. So, quite clearly the expression we just now derived, assuming gray diffuse isotropic surfaces, is not quite accurate, and we need to look at an alternative derivation. Now, in the new derivation now, we take into account the fact that the spectral emissivity of metals, because the outer surface or the inner cylinder of the Dewar flask and the inner surface of the outer cylinder are both silvered. Silver is a metal, and for that we can assume that the emissivity is a constant times temperature of that surface divided by lambda to the power of 0.5. So, this is the expression which we had earlier looked at and showed how it affects both the total emissivity and the total absorptivity of metals. Now, we are going to use this result, and now the expression for heat transfer in wavelength range lambda to lambda plus d lambda will now become, as an extension of the previous derivation for gray surfaces, this is now non-gray surface, can be written as epsilon lambda 2 epsilon lambda 1 into E lambda 2 times divided by this quantity. So, this result is very close to what we derived. Let me just remind you that this is not very different from what you got. Let me just remind you that if the surfaces are gray, then Q12 could be written like this. So, this expression you write, but if it is non-gray, then Q12 becomes 0 to infinity E lambda B1 minus E lambda B2 divided by 1 by epsilon lambda 1 plus 1 by epsilon lambda 2 minus 1. So, this expression will be same as the expression above if these quantities are independent of wavelength and you can take it out, then we integrate this to get that result. Now, we cannot do that because we just now saw that epsilon lambda goes as b into root t by lambda. So, epsilon lambda is a function of lambda. So, we have to do this integration very carefully to get the right result. And notice this result at the top can be written as similar to what we had discussed for convection. So, this, if you treat this quantity as not a strong function of temperature, then this is what is called the radiative heat transfer coefficient. So, this kind of result is used frequently by many people, and it is quite adequate in those situations where the surfaces are gray. But when you come to a non-gray surface like a metal, this is not going to work, and we saw that the observation with Dewar flask show clearly that the heat transfer rate is not proportional to the temperature difference. So, this is the point we want to look at further. So, this expression which I had written earlier. Now, if you integrate that expression for the spectral flux, assuming the emissivity to be b times root t by lambda, then you will get the following expression for the net radiation. Notice that this is very different from the simple expression involving t to the power of 4 that we obtained for gray diffuse isotropic surfaces. This is much more complicated, involves T1 to the power of 5, T to the power of 0.5, T to the power of 5 and so on, and you won't expect this expression to show a simple dependence of heat transfer rate to delta T. So, here I have given a typical number for a silver surface. So, we have to calculate this for a case when there is hydrogen, when T2 is 20 degrees Kelvin, for 1977. In both cases, T1 will be taken as ambient temperature. And if you take this equation and remember the fact that if T1 is about 5 to 10 times larger than T2, so T1 to the power of 5 will be much greater than T to the power of 5. So, we can neglect these terms, and so then you take the ratio of heat transfer to nitrogen to heat transfer to hydrogen, then you will get this kind of number, which will come out as around 1.63. So, this is very close to the observations which indicated that heat leakage to nitrogen was about 60% more than that to hydrogen. So, this simple non-spectral non-gray approximation has going to result very close to the observation, and this clearly shows that this is the approach we need to take, because if we had not taken this approach, but had assumed that the emissivity is not a function of wavelength, that is a gray surface, then you would get a number less than 1 here, because you would then assume that heat transfer is proportional to delta T. Now, to make this point even more dramatic, we take up the case of the Dewar flask, where the outer cylinder has a 300 K, and I vary the temperature in the cylinder such that delta T, when the inner cylinder is 0 degrees Kelvin, delta T is 300, when the inner cylinder is 300, delta T is 0. So, if the inner cylinder is 300, of course, there is no heat transfer, because the temperature of the outer and the inner cylinder are same. Okay. And as you start reducing to the inner cylinder, the heat transfer will go up, and you see that up to around 150 Kelvin, the heat transfer keeps going up, but then something unusual happens. As the temperature difference goes beyond 150, the heat transfer starts coming down. So, this is a portion which is of great interest to us. This is a portion where if you store liquid oxygen or liquid nitrogen or liquid hydrogen, you will be in this part of the curve. So, in this part of the curve is where, as the delta T increases, the heat transfer goes down. This is the result which is counterintuitive, which does not follow the traditional heat transfer texts, which say that as you increase delta T between two surfaces, the heat transfer should go up. Here it is going down. Okay. And to the point that if the inner surface was really at 0 K, then heat transfer is almost 0. Okay. All the delta T is of the order of 300 K. So, this is a point which is really worth understanding, that when the temperature difference is small, then roughly the heat gain is proportional to delta T. But when the temperature of the inner cylinder becomes very, very low, below 150 K, you start seeing another domain in which the heat transfer is going down as delta T is going up. And this can only be explained by the fact that the relation between heat transfer and temperature in the case of radiated heat transfer is quite complicated, especially when the two surfaces are not gray, but metals, and because of the spectral variation of emissivity with temperature and wavelength, we get an unusual result. Now, the simplest way to understand this is the impact of emissivity and temperature. If the inner cylinder is truly at 0 Kelvin, according to this equation, emissivity is 0. Now, strictly speaking, you cannot use this equation when temperature approaches 0, because the phenomena that of radiation that occurs at such low temperatures is somewhat different from what was assumed in obtaining this equation. But still, you can assume that although this actual equation may not be valid, that as the temperature goes to 0, emissivity will indeed tend to 0. And so, this is one important feature, and this is the primary reason why the heat transfer to hydrogen Debye flask is lower than that of nitrogen, because hydrogen is at 20 K, and at 20 K the emissivity is about 1/4 of the emissivity at not for half of the emissivity at 77 K. So what really happens is that the Debye flask containing hydrogen, being at a lower temperature, absorbs about half the radiation compared to the Debye flask containing liquid nitrogen, mainly because emissivity decreases with temperature. That is the main. But if you really want to account for all other phenomena occurring there, including changes in how the emissivity, whereas we take all into account, you get this 60% change. Otherwise, you should get around 2. Because of temperature change alone, the emissivity of the inner surface, which is equal to absorptivity, assuming the surface is diffuse isotropic, then the Debye containing liquid hydrogen should absorb about half of the radiation emitted by the outer surface in comparison to liquid nitrogen, primarily because of this effect. But if you take into account both the temperature effect and the wavelength effect, then one can show that the result will be somewhat more complicated than which we saw here. Okay. So, this is a very good example showing how radiation heat transfer behaves in ways somewhat paradoxically, mainly because of the spectral variation of radiative properties, which can alter the general rule that heat transfer is proportional to temperature difference. And so, we saw the interesting example that as the temperature of the inner cylinders keeps falling, the heat transfer rate keeps falling, although the delta T is going up. And this is related to the fact that emissivity is a function both of temperature and wavelength, and that plays an important role. So, by looking at the non-gray nature of the radiative properties, we are able to explain this unusual feature of radiation transfer, which is quite different from what one encounters in either conduction or convection transfer. Now, I want to take another example of the spectral variation of properties having an influence on temperature by looking at temperature control in space through use of selective surfaces. We had talked about selective surfaces earlier as surfaces whose radiative properties varies dramatically in 2 different wavelength ranges. So, I have taken a very simple example in which the emissivity of a surface is a large value, is of one value for a wavelength below a cutoff wavelength called lambda c, and above that it is a totally different value. So, there is one wavelength at which the property changes dramatically, and this is seen quite often when you coat a semiconductor on a metal. The semiconductor's properties will emerge in this region, while the properties of the underlying substrate metal will be appearing in this region, and this unusual sharp change in the radiative property is related to the way in which radiation is absorbed in a semiconductor. Now, such surfaces are used quite frequently in satellite to control temperature of the surface. In a satellite, there may be a requirement to have the temperature of surface being very high or very low. Very high would be in applications where you are trying to generate power in a satellite using a high temperature source. So, in that case you want to maintain the temperature of the surface very high. That means, you want to absorb as much of the solar radiation as possible from the surface, and at the same time reduce the emission of the surface, so that the surface remains hot. So, this is commonly also useful in solar collectors, where you want to get a very high temperature. So, you want your collector surface to absorb radiation in the solar region, which is between 0.4 micron and 4 micron, but at the same time you do not want the surface to emit much radiation, and most of the radiation emitted by the surface is usually in the range between a few microns to 100 micron. And so, you choose a cutoff wavelength somewhere around 4 micron, so that you maintain the emissivity of surface low in the region beyond a few micron. At the same time, in the region where solar radiation is incident, the low wavelength region, you try to maintain a high emissivity and high absorptivity. So, this is the purpose. Let me just write down the energy balance for this case. Yeah. So, let me write down the energy balance for this case. Now, I am taking a very simple case of a flat plate insulated here and subjected to solar radiation. So, this is solid surface we are talking about. So, the energy balance will tell you that Q sun, and we already indicated that our solid surface will be one in which it will have one emissivity at one wavelength, and at some cutoff wavelength the emissivity will go down to epsilon 2. So, that is the case, then the total energy absorbed will be the amount of radiation lying in this region 0 to lambda c plus the amount of radiation lying in the remaining on the right. So, this region, this has to be equal to the heat lost by the surface, which will be epsilon 1 F 0, this is T sun here, this is 0 to minus lambda c T of the surface, not the sun, that is sun, and epsilon 2 into 1 minus F into 0 to lambda c T surface into sigma T surface to the power of 4. This is the main balance. We have neglected here the cosmic background radiation coming on the surface. We will include that subsequently, because that is very small. So, the only two processes that is occurring is photons coming from the sun are being absorbed by the solid surface, and at the same time solid surface is emitting radiation depending on its temperature T s. Our aim is to find T s as a function of this cutoff wavelength lambda c. Okay. We want to know what is the best value of lambda c, which gives the highest temperature. This could be an application where you are trying to generate power on a satellite using a high temperature surface as the heat source, and you want to know what is the appropriate cutoff wavelength. Okay. So, this problem can be solved easily, but of course, since you have to calculate these quantities, you have to integrate the function numerically. These have to obtain numerically, and this equation is nonlinear. So, there is no simple analytical solution available to you. So, this is solved numerically using standard software, which calculates these integrals and then assumes the value of T s, which will get you this balance. Okay. So, let us see what we get. So, this is the problem, and here at the top you see this is the equation. This is called equilibrium temperature, the surface temperature of the solid surface, and what we have shown here is how the equilibrium temperature surface depends upon the cutoff wavelength, varied from 0.001 micron to 10 micron, steps of 0.1 micron, solved numerically. And I have taken various cases, one in which the emissivity is 0.1, 0.9 in the solar region and 0.1 in the infrared region, and I have gradually increased this value to close to 1 and this one very close to 0. You realize in this case you can make it exactly 0, because if the emissivity of the surface is exactly 0, then it cannot have a steady state temperature, because then it cannot get rid of the heat, and so whatever heat is absorbed cannot be lost. So, temperature will go on increasing. So, you have to keep this non-zero. So, you kept a very low value, and you can see the lower the value, higher the temperature. So, in this example, we have gone from a value when emissivity is 0.1, we have value close to 600 degrees Kelvin, and as you reduce the emissivity of 0.1 onwards to very low values, this temperature is going up and is increasing and has gone up to 2100 degrees Kelvin. And as you take emissivity lower and lower, it will keep going up. Okay. And as all of you probably realize, the highest value it can go to is of course the sun's temperature, which is assumed to be 5800 Kelvin. We assume sun to be a black body at 5800 degrees Kelvin, and so highest you can attain, if at all, is that number, but you won't get anywhere near it unless you make this extremely very small. Now, the reason why this temperature increases so rapidly as you reduce the cutoff wavelength is because of the fact that the amount of radiation coming from the sun is around 1365 watts per meter square. This is quite large. Okay. So, if you recall from the previous lectures, the sun's radiation lies mainly between 0.4 micron and 4 micron. If you keep the cutoff wavelength at 4 micron, you see that the temperature that you get is around 600 K, whatever the values of these emissivities. So, what it means is that at 4 micron, the high emissivity in this region is leading to sufficiently high losses from the surface, the temperature cannot really go beyond 600. So, you need to push the cutoff wavelength to lower wavelength, of course, which ultimately will reduce the amount of solar radiation absorbed. That is why you go to too low a value, like around less than a micron, then you can see temperature falls sharply, because you are not absorbing sufficient amount of solar radiation in order to attain high temperature. So, there is a trade off between using a very high lambda, which causes some of the emission from the surface to be in the region below that cutoff wavelength and lose heat. So, to avoid that, you have to reduce the lambda c, but if you reduce lambda c to too low value, then the sun's radiation plays a role. So, this line represents the optimal wavelength at which you are able to attain the highest temperature, and this depends of course on the emissivity epsilon 2 on this side, that is depends on this emissivity, because this determines how much heat the surface is losing. So, if this can be kept very low, you can reach as high temperature as you can. As said, theoretically the temperature you can reach is about 5800 degrees Kelvin, which is sun's temperature. You cannot exceed sun's temperature, because if we did, you will violate the second law of thermodynamics. Now, you might ask why we did not go to lower temperature, lower emissivity values. Actually, there is a problem with numerical convergence as you go to very low emissivities, and so you need more and more accurate numerical scheme to calculate these f0 lambda t values. So, these are obtained by numerical integration, and those integrations have to be pretty accurate to 6th or 7th or 8th decimal place for you to get the right values. So, that is the main touch. Now, let us look at the next example. Now, here let me read it. This is the equation we wrote for, in this case I am trying to keep temperature cool. So, in this case we think of application in space where a certain surface has to be kept cool although it is absorbing solar radiation. So, here I want to make the problem a little more complicated. Here is the flat surface, it is subjected to sun's radiation. It is also subjected to radiation from all around. This is known as cosmic background radiation. Okay. This is from black body at around 2.72 degrees Kelvin. Okay. This was discovered about 50 years ago, and this is radiation coming from the all around from the universe, and it is very close to a black body at about 2.72. Normally, we will ignore this kind of temperature, they are so low, but in this present example, where we are trying to keep the surface at low temperature, we have to account for it for completeness sake. So, in this case, the radiation absorbed will be from the sun, which will be epsilon 1 times f 0 to lambda c sun plus epsilon 2 f 0 to lambda c, I am sorry, 1 minus plus the second term here is from the cosmic background radiation, which will be sigma T c to the power of 4. Here it will be epsilon 1 f 0 to lambda c T cosmic plus epsilon 2 into 1 minus f 0 to lambda c T cosmic. These are the two terms of the incoming radiation absorbed by the surface. This has to be the emission. Emissivity of the surface now is going to be epsilon 1 f 0 to lambda c T equilibrium temperature surface plus epsilon 2 into 1 minus f 0 to lambda c T equilibrium into sigma T equal to the power of 4. So, we want to find what is the equilibrium temperature of the so called radiative equilibrium temperature, that is the temperature attained by surface purely from radiative balances. So, this quantity as a function of the sun's radiation and the cosmic background radiation. Of course, you would expect that this will play a very important role, because radiation emitted by the sun is 1365 watts per meter square. This will be very, very low, because at a temperature of around 2 degrees Kelvin, the radiation coming into the surface is very small. We still retain it, because in the limiting case wherein we are able to prevent absorption of any solar radiation, this term will begin to play a role. So, here our aim is to find that lambda c which give you the lowest temperature. So, we want to find out T equilibrium as a function of the cutoff wavelength, and in this case we are interested in that cutoff wavelength at which the temperature of the surface is the lowest, because this application we want to minimize the temperature of the surface, not maximize it like we had last time. So, again you have to solve this equation numerically, because all these factors f 0 lambda factors here are all obtained by accurate numerical integration. We know these two quantities, we know everything except T equilibrium. So, this problem is solved iteratively. You assume some value of T equilibrium and see whether the left hand side right hand side balance. If they do not, you adjust it until they come to balance. So, this is a process of iteration, has to be done carefully and accurately, because some of the numbers are quite small, but they are still very important. So, this is best done with commercial software available today in most computers and institutions. So, you use this to solve this problem iteratively. It is a good exercise in numerical analysis to solve this equation, because it is highly nonlinear. So, it requires some kind of expertise as well as intelligence to ensure that your methodology converges quickly. So, I suggest that you take it up and see how good it is. Let me just show you the answers that we got. This is the variation of the equilibrium temperature with the cutoff wavelength. Now, the cutoff wavelength is varied mostly from around 10-20 microns to 1000 micron, because you want to reduce the absorption of solar radiation in order to keep the surface cool. So, your cutoff wavelength has to be as high as is possible, and you can see that as the cutoff wavelength is increased from around 10 microns all the way to 1000 micron, the minimum temperature, which is the dotted line here, goes on decreasing and ultimately will reach 2.72 degrees Kelvin asymptotically. But before that, notice this interesting feature, that if your surface had, let us take the green one, emissivity only 0.0001 in the solar region, but a very high emissivity in the region beyond lambda c, then you see that you get this kind of curve. That is, when lambda c is 0 or very large, in both cases the temperature is close to 393 Kelvin. The 393 Kelvin comes in if the emissivity is, so if you had a gray surface, then your equation will be q sun epsilon sun is equal to, I am sorry, q sun epsilon surface is equal to epsilon surface sigma T s power 4. So, you can solve this equation very easily, and you get that for q sun of 1365 watts per meter squared, you will get T s is 393 degrees Kelvin. Okay. So, this is a solution when emissivity is not a function of wavelength. So, this happens for lambda c of 0 and lambda c tending to infinity. In both these cases, the if you recall lambda c tending to 0, then you will have only equal to epsilon 2. So, this is a general function. So, lambda c goes 0. On the other hand, if lambda c tends to infinity, you have only epsilon 1. So, both these are gray surfaces. For gray surface, this cancels out, epsilon surface. So, you are left with a very simple balance from which you will get this number. Okay. Now, let us go back to the result we saw here. So, in both these limits, very low lambda c and high lambda c, the temperature approaches that 393 value. In between, it reaches a minima, and in this present case, for this particular case, for example, it reaches at about 100 micron. At 100 micron, what you are able to do is, you are able to keep the amount of solar radiation that is absorbed by the surface to a minimum, at the same time keeping the radiation emitted by surface highest. Only when you do that, you get a minimum value which is around here 25 Kelvin. But if you really take this case where emissivity in the region 1 below lambda c is 0 and the emissivity at the higher region is 1, then the minimum temperature goes on decreasing, and if you do your computation accurately, ultimately you will reach a temperature of 2.72 degrees Kelvin, which is the temperature of the cosmic background radiation. So, that is the result that you get in this case. So, these are very interesting problems, and the unusual behavior you see here is primarily on account of the non-gray nature of the surface, both in the case of Dewar flask as well as in this case of selective surfaces used in solar in space applications. You see some unusual behavior because of the fact that we allow for the variation of spectral properties with wavelength. So, that brings in rather interesting issues into play, and so these two examples were brought in just to show that there are situations wherein the variation of emissivity and absorptive wavelength can get you a very paradoxical result, or results which are counterintuitive because of the strong variation of the property with wavelength. So, these are two examples which I want to take up. Now, before we move on to detailed treatment of the how to treat non-radiative non-gray surfaces, I will give one more example of non-gray nature of surface. This is in the design of tungsten filament lamp. For more than 100 years, this was a traditional lamp used for lighting houses and industries. Of course, today slowly this lamp is getting phased out, primarily because these lamps are not very efficient. Typical tungsten filament lamp converts around 5 to 8% of the electrical energy consumed into visible light. Tungsten filament lamp emits mostly in the infrared. So, tungsten filament lamp is not a good way to get light energy. It is a very efficient way to get energy for heating. Infrared radiation, for example, is used in industry for infrared heating of various materials, but it is not a very good source of visible light, and this is because tungsten is a material whose melting point is 3655 degrees Kelvin. So, when you use tungsten filament lamp, you have got to ensure your temperature is sufficiently below this, so tungsten does not evaporate and disappear. So, the challenge in design of the tungsten filament lamp is to keep the temperature sufficiently low, so that it does not lose material rapidly, but at the same time the temperature has to be high enough that is sufficient radiation in the visible. So, this is the challenge. So, if you keep the temperature too low, then most of the radiation will be in the infrared and not enough in the visible. So, in order to get a lamp which gives sufficient visible light, we need high temperature of the filament, but a too high temperature will lead to destruction of the filament because of evaporation, or actually strictly speaking sublimation. So, this trade off has to be there. Now, the tungsten filament lamp is not a gray surface, and this is best illustrated. We look at the emissive power of the tungsten filament lamp measured in the laboratory in watts per centimeter square. Empirically, you see it is around 160.5 into T by 3000 to the power of 4.48. So, notice that it is not to the power of 4, which is true for a gray body or black body. It is somewhat different. It is not like a true metal. A true metal, if it is a metal as in the manner in which we discussed the property of the metals, then emissive power should go on to the power of 5. Okay, emissivity is proportional temperature, but it is not following that. Black body is to the power of 4. So, tungsten material is somewhere between black and metal behavior, in between 4.5. So, that is one part, but the real issue in the tungsten filament lamp is the way in which it loses material by sublimation. The sublimation rate, that is conversion from solid to vapor, has been measured in grams per centimeter square per second, and it is typically 10 to the power minus 6 into T by 3000 to the power of 30. The huge power, that is, as the temperature increased even 1 or 2 degrees, the sublimation rate goes up as T to the power of 30. So, this is really what is going to control the design, because if the temperature goes up too rapidly in the design, then the sublimation rate goes up very rapidly and hence the life goes down. So, as the temperature of the filament increases, life will go down very rapidly. And so, this is the challenge that is faced by the design of the tungsten filament lamp, is to maintain the lamp temperature sufficiently high to ensure that there is more radiation in the visible, but at the same time keep the life high. So, how the design done? Essentially, the design involves realizing that the power consumed by the filament is V squared by R, and the power radiated, this is the power generated by electrical heating, is radiated is epsilon filament sigma T filament to the power of 4 into area of the filament, which is pi d L. These two have to be equal at equilibrium, neglecting conduction and convection. At the same time, you must remember that the resistivity of the tungsten filament lamp in ohm centimeters is 92 ohm centimeter at the standard value of 3000 degrees Kelvin to the power of 1.2. So, this also has to be accounted for. So, once you know the temperature of the filament, you calculate the resistivity, from there you calculate the resistance, then you know the power generated, that has to be equal to the power radiated. So, there are two unknowns here in this problem. And the two unknowns are the length of the filament and the diameter of the filament. And you will find when you do the design for a typical lamp, the diameter may be of the order of 1 to 10 micron, and the length will be of the order of centimeters. So, in order to build, you do what is known as coiled coil. So, the thin filament is coiled many times to get the large length that is required within that small lamp. So, this is a coiled coil that you arrange inside the lamp, and you can see that the tungsten filament lamp demands a very precise manufacturing technology, because the diameter of filaments are very low. So, any error in manufacture will cause a short life of the lamp. So, here is an example where electrical engineering and heat transfer engineering are interacting in the design of a filament lamp, and the design is very sensitive to the details of the emissivity of the filament and the resistivity of the filament. So, this illustrates how many other problems in real engineering are interfaced between many subjects. So, today we have given a few examples, and we will continue in the next lecture with some more examples.